There are some earthquakes that announce themselves like a freight train. Windows rattle, concrete groans, cars bounce. People know immediately that something enormous has happened. And then there are the other ones, the strange ones, the ones that do not seem to match the disaster they are about to unleash. That is the story we are looking at today. An earthquake struck off western Indonesia near the Mentawai Islands. And the first seismic number looked serious but not world-ending. The shaking in some places felt strong. In others, it felt oddly muted for what came next. If all you had was the first impression from the ground, you could have talked yourself into believing the danger was already passing. But here's the part almost nobody understands until after a tragedy like this. The earth does not only speak through shaking, it also speaks through the ocean. And when the ocean started reporting back, the picture changed. Sensors far from shore began recording a wave train that told scientists something deeply unsettling. This was not just a normal offshore earthquake. This was the kind of event that can hide some of its true danger in the first few minutes, then reveal it through the sea itself. I want to be very careful with the language here, because this is where hype channels usually lose the plot. No scientist had a magic prediction. No secret lab knew exactly what the next shoreline would look like before the earthquake happened. But once the rupture began, once the seabed moved, there were real measurements that started filling in the blanks. Ocean sensors, tide gauges, and tsunami models began to show that the wave behavior was larger than you would expect from the magnitude number alone, and that difference matters. It matters because people near the coast do not die from a magnitude on a screen. They die from what the water does next. They die when the first clue seems manageable, but the second clue arrives too late. So if you have ever wondered how one earthquake can feel smaller than the disaster it creates, or why some tsunamis hit harder than the first shaking suggests, stay with me. Because this is one of those events where the ocean became the witness, the alarm, and the explanation all at once. The earthquake was the October 25, 2010 Mentawai tsunami earthquake off western Sumatra, Indonesia. NOAA's Center for Tsunami Research describes it as a magnitude 7.7 event west of Bengkulu, and notes that the tsunami was first recorded at Buoy 56,001 in a little under 2 hours and at Buoy 56,003 in a little under 3 hours. On that same official event page, NOAA states that the DART data and model inversion indicated the tsunami may have been larger than the earthquake magnitude of 7.7 suggested. That is the sentence that changes the whole story. A magnitude 7.7 is already a major earthquake. But when the sea tells you the tsunami is behaving like something bigger than the basic shaking number implies, you are no longer dealing with a routine event. You are dealing with a special class of earthquake that disaster scientists have a very specific name for, a tsunami earthquake. Let's start with exactly what that means, because the phrase sounds backwards. Every big seafloor earthquake can potentially produce a tsunami, but a tsunami earthquake is different. It is an earthquake whose shaking can seem weaker than expected, while its tsunami is larger than expected. In other words, more of its destructive power goes into moving the seafloor and the water above it, and less of it goes into the kind of high-frequency shaking people instinctively fear on land. Imagine two people pushing the same heavy table. One slams into it quickly and loudly, making a huge bang. The other leans slowly and steadily, sliding the whole table farther across the room. Both involved force, but the second one moved the object more efficiently. That is a rough household analogy for what can happen with a tsunami earthquake. It can rupture more slowly, closer to the trench, and over very shallow parts of the plate boundary, pushing a lot of ocean water without broadcasting the same kind of violent short-period shaking that screams danger to every person on shore. That is one reason events like this are so deadly. Human beings are not bad at sensing immediate danger. We are bad at sensing mismatched danger. If the house shakes like crazy, people panic. If it rocks more gently or for less time than expected, some people decide to wait. They go outside, check their phones, gather family members, or look toward the beach. But near a tsunamigenic coast, even a minute or two of hesitation can cost lives. No rumble, no wall cracks, no obvious cinematic warning on the horizon. Then the ocean arrives. That is why coastal tsunami education does not begin with a siren, it begins with a rule. If you are near the shore and you feel strong or long shaking, or even unusual shaking during an offshore event, move immediately to high ground. Do not wait for somebody to explain whether it was strong enough to count. Nature does not grade your test before the water comes in. To understand why the Mentawai event mattered so much, we have to leave the villages and go under the sea. Western Indonesia sits above one of the most dangerous tectonic boundaries on Earth. The Indo-Australian plate is diving beneath the Sunda plate along the Sunda megathrust, a giant subduction zone that has generated some of history's most destructive earthquakes. This is the same broader system that produced the 2004 Indian Ocean earthquake and tsunami, but not every part of the subduction zone behaves the same way. Some sections rupture in ways that produce obvious, monstrous shaking and broad destruction. Other sections, especially near the trench, can rupture more slowly and in softer sediments. When that happens, the seismic waves that make the earth feel violent may not be the whole story. The quieter part of the rupture can still shove a huge volume of seawater upward. Here's another way to think about it. If you smack the side of a bathtub, you make noise and splashing. But if you slide your hand under the water and slowly lift a large tray, the water surface rises across a wider area. A tsunami earthquake is not gentle in any human sense. It is still a major rupture, still deadly, still powerful beyond anything we can imagine in everyday life. But from the standpoint of seismic fingerprints, it can be deceptively soft-spoken. That is why the first magnitude estimate does not always tell the whole truth about the coastal hazard. Scientists know this, warning centers know this, but the public often hears one number, assumes they understand the threat, and misses the fact that the ocean itself may deliver the more important update. That brings us to the sensors. And the DART system, which stands for Deep Ocean Assessment and Reporting of Tsunamis, is one of the great quiet achievements of hazard science. A DART station uses a seafloor pressure recorder and a surface buoy to detect tiny changes in water pressure that reveal the passage of a tsunami wave. The important part is this. In the open ocean, a tsunami may only be inches high. To a ship on the surface, it can be almost invisible. To a deep ocean pressure sensor, it is a real measurable signal. So while the first earthquake alert comes from seismometers, the truth check often comes from the water itself. The warning centers model what the tsunami should look like, and then compare that forecast to what the sensors are actually recording. If the observed sea level signal is higher, broader, or differently timed than expected, the understanding of the event changes in real time. In the Mentawai case, NOAA's event page lays this out with unusual clarity. The tsunami reached Padang in about 65 minutes after the earthquake. It was then recorded at the DART buoys, and the DART-based source inversion suggested a tsunami larger than the plane. Magnitude estimate implied that is not just a technical note for researchers. That is the entire drama of this title. The quake came without an obvious warning of how disproportionate the wave might be. Then the ocean sensors detected something much bigger than the first seismic shorthand suggested. The earthquake and the tsunami were telling two parts of the same story, and the second part was the scarier one. Now, I need to pause here for the honesty pivot, because this is exactly the place where bad disaster content says things like, scientists knew the big one was coming, or the ocean exposed a hidden megaquake. That is not the real story. Anyone telling you they can predict the exact size and local impact of a tsunami before the data come in is not being honest with you. The real story is not fake panic. The real story is that warning systems are designed for uncertainty. A major offshore quake happens. Seismic networks estimate the location, depth, and size. Tsunami centers run models. Ocean sensors and coastal gauges begin reporting. Scientists compare forecast to observation, and then they update. And that process can look messy to people who want instant certainty, but the messiness is actually a sign that the system is doing its job. And here's the part that gives me chills. The difference between a false sense of safety and a life-saving evacuation can come down to whether people understand that warnings are not admissions of ignorance. They are decisions made under incomplete information, because waiting for perfect certainty can be fatal. In a local tsunami, the first wave can arrive in minutes. In the Mentawai region, some coastal communities had almost no time. The hazard was not simply that a large earthquake had occurred. The hazard was that the kind of earthquake that had occurred was unusually efficient at making a tsunami. This is why the phrase tsunami earthquake exists at all. Scientists needed a term for events where the oceanic consequences are out of proportion to what many people would expect from the felt shaking. The classic examples go back decades. The 1946 Aleutian event generated a devastating Pacific-wide tsunami and is one of the historical cases that pushed warning science forward. The 1992 Nicaragua event is another famous tsunami earthquake, where people who were used to judging risk by shaking intensity learned a brutal lesson. Those cases matter because they show a repeating pattern. The ground message and the ocean message do not always match. When they do not match, the ocean message can be the one that kills. The human side of the Mentawai disaster was heartbreaking. Villages on the outer islands were hit hard. Homes were torn apart. Boats were carried inland or smashed. Whole communities that had survived the shaking found themselves directly in the path of fast incoming water. Hundreds of people were killed, injured, or left missing in the aftermath, and many more were displaced. The remoteness of the islands made everything harder. That is another detail that gets lost when people talk about warning time as if it were the same as escape time. A community can receive a warning and still have terrible odds if the roads are poor, the high ground is far. The geography channels the wave, and people are asleep or isolated when the event begins. Think about what a local tsunami asks of a coastal village. In the space of minutes, people have to recognize an unusual threat, trust that it is real, gather children or older relatives, choose the right direction, move fast over uneven ground, and do it all without stopping to collect too many possessions. There is no pause button. There is no clean split between earthquake phase and tsunami phase. In some of the worst events, the psychological transition is the killer. People mentally file the earthquake under "that was scary" and do not switch quickly enough to "I need to run uphill right now." That is why tsunami education drills such a ample message. Do not debate with the coastline. Leave. There is also a bigger scientific pattern worth understanding here. The slow, shallow part of a subduction zone near the trench can be especially dangerous because it is close to the ocean floor. When rupture happens there, even if it radiates seismic energy inefficiently, it can still produce a lot of vertical displacement. And vertical displacement of the seafloor is exactly what launches a tsunami. If a fault moves mostly sideways, the ocean may respond less dramatically. If a fault lifts or drops the seafloor over a broad area, the water above it is displaced. From there, physics takes over. In the deep ocean, the wave may stay low but move fast, sometimes at jetliner-like speeds. As it reaches shallow coastal water, it slows down, piles up, and can grow dramatically in height. This is why ocean sensors matter so much. They help bridge the gap between theory and reality. A model can tell you what should happen if the rupture looked a certain way. A dart buoy can tell you what the ocean actually did at a specific point. Put enough of those observations together, and the event starts to reveal itself. It is like hearing a voice in a dark room, then slowly turning on more lights. The first signal tells you someone is there. The later signals tell you who it is and what they are doing. In tsunami science, every extra observation can refine the forecast downstream. And that is not just useful for the source country. Tsunami science is fundamentally a network story. A wave generated near Indonesia can become a local catastrophe there and still be a distant concern for other coastlines. Around the Indian Ocean and beyond, travel times differ, wave heights differ, coastline shapes differ, but the principle is the same. The farther the wave has to go, the more opportunity scientists have to check the sea level data and update the forecasts. That is why ocean observations are such a powerful public safety tool. They turn the ocean from an unknown into a measured system. For viewers in the United States, especially in Alaska, Hawaii, Washington, Oregon, and California, the lesson is extremely practical. A far-field tsunami gives warning centers more time. A local tsunami gives you less. If the source is across the Pacific, dart buoys, coastal gauges, and models can help emergency managers refine the threat as the wave travels. If the source is right off your coast, the natural warning may be the only warning you get in time. Strong shaking, long shaking, sudden sea withdrawal, a loud ocean roar. Those are not just interesting facts for documentaries. They are survival information. I am not telling you a giant Pacific tsunami is guaranteed. I am telling you the ingredients that make certain coasts dangerous are already known. The same tectonic logic that threatens Indonesia also applies in different ways to Alaska and Cascadia. Offshore subduction zones are capable of creating earthquakes that produce both strong shaking and tsunami danger. And in the worst local cases, there may not be enough time to wait for a phone alert before moving. That is why preparedness planners in U.S. coastal communities put so much effort into evacuation maps, school drills, vertical evacuation structures, and public signage. The science is not abstract. It is a race against minutes. Let's go back to Mentawai for a moment, because the event also teaches a lesson about measurement itself. Earthquake magnitude is not fake. A magnitude 7.7 or 7.8 event is huge, but magnitude is one summary number. It does not tell you everything about rupture depth, rupture speed, or tsunami efficiency. Two earthquakes with similar magnitudes can produce very different consequences. One may shatter buildings far inland but create a modest tsunami. Another may produce less dramatic felt shaking in some places yet send a disproportionately dangerous wave into nearby coasts. This is one of the most important mental upgrades a viewer can make. Stop treating the magnitude as the full story. It is one chapter, not the ending. The same is true of warning language. People hear, watch, advisory, or warning and assume each word reflects absolute certainty. It does not. It reflects a combination of observed data, forecast confidence, and public safety decision-making. Scientists are not fortune tellers. They are evidence managers under time pressure. When the evidence says the ocean may be doing more than the first seismic estimate suggested, the responsible move is caution, and if later data reduce the threat, that does not mean the earlier caution was wrong. It means the system gathered enough evidence to refine the danger. In the years since the Mentawai disaster, warning science has continued to improve. DART networks, GPS, better modeling, faster communications, and stronger links between monitoring agencies and local responders all make a difference, but the weakest link is often still human behavior. An alert cannot carry your grandmother uphill. A buoy cannot force a tourist off the beach. A model cannot make a sleepy fishing village outrun a wave if no one believes the danger is real. Technology saves lives only when it connects to trust, education, and practiced action. This is why I think tsunami education should be emotional as well as technical. People need to understand the mechanism, yes, but they also need a vivid memory that overrides hesitation. If you are on the coast and the ocean is part of the story, do not wait to be impressed by the earthquake before you respect it. Some of the worst tsunami earthquakes do not perform the way your instincts expect. They do not always feel like the cinematic monster in the first seconds. The monster may be the water that follows. There is another hidden danger in stories like this: rumor. After a tsunami earthquake, social media often fills with claims that a second giant wave is definitely coming, or that a bigger quake has been triggered and will strike a specific hour later. Here is the part that changes everything. Good science can tell you what happened, what is being observed, and how the risk is being managed. Good science cannot give you exact prophetic certainty about the next major rupture. Aftershocks can occur, hazard conditions can change, but anyone assigning a guaranteed time and place to the next big event is guessing. And in disasters, guesses dressed up as certainty can get people hurt. So what should you actually watch in an event like this? Watch the official earthquake location and depth. Watch whether the event is offshore and likely to involve vertical seabed movement. Watch official warning center messages, watch sea level observations if you know how to read them, or follow trusted summaries from agencies that do, and watch for local natural warning signs. And if you live in a tsunami zone, know your route to high ground before you need it. That is not fear, that is calm preparation. One of my favorite phrases in hazard science is simple: the ocean is the truth test. Seismometers may tell you that a rupture happened. The ocean tells you how much of that rupture translated into tsunami. Energy. In Mentawai, the ocean sensor showed a signal that pushed the scientific interpretation toward a larger tsunami source than the magnitude alone implied. That is the heart of this story. The quake came without the kind of warning many people psychologically expect, and then the water itself reported something more dangerous, and the ocean can be brutally efficient at carrying that truth. In deep water, tsunami waves are long. Their energy is spread through the full water column. They are not like normal wind waves that break and dissipate quickly. They travel, they wrap around headlands, refract over underwater ridges, and sometimes focus energy in ways that make one bay far more dangerous than the next. That is why local geography matters so much. Two villages on the same island can see very different outcomes depending on orientation, offshore bathymetry, elevation, and distance from a source. This is also why post-event fieldwork matters. Scientists do not stop when the warning ends. They go out and measure run-up marks, debris lines, erosion patterns, structural damage, and survivor accounts. They compare those observations with buoy records and model outputs. They ask whether the rupture reached unusually close to the trench. They ask whether the largest slip occurred shallower than expected. They ask whether coastal topography amplified the wave in certain places, and all of that work becomes the next generation of public safety. In a very real sense, every major tsunami teaches two audiences at once. It teaches scientists how to model better, and it teaches communities, sometimes painfully, how little time the ocean may leave them. The tragedy is that those lessons are often learned in blood. The opportunity is that they do not have to stay there. When a warning map gets improved, when an evacuation route gets moved, when a school drill gets taken more seriously, the memory of one disaster becomes protection for the next town. Here's another way to think about it. A tsunami warning system is not one machine. It is a chain. At one end of the chain is the earth itself, tectonic plates, faults, trenches, the shape of the seafloor. Then come the instruments, seismometers, dart buoys, tide gauges, GPS. Then the analysts, forecasters, and models. Then the emergency managers. Then the road signs, the school teachers, the local officials, the family decisions, the person carrying a child uphill in the dark. If any one link breaks, the water does not care. So when we say scientists are watching, we should picture the whole chain, not one person staring at a blinking screen. And yes, there is a hopeful side to this story. The fact that ocean sensors could detect the tsunami and help refine the source means we are not as blind as coastal societies once were. The fact that NOAA could publicly note that the dark data implied a tsunami larger than the magnitude suggested shows how far warning science has come. The fact that we can compare this event to 1946 and 1992 and others means the pattern is recognized. We are not guessing from scratch every time. The Earth keeps surprising us, but it does not do so in a total vacuum. Still, the surprise remains emotional. A quake you might have mentally filed under serious but survivable becomes, to the evidence of the sea, the opening act of a much more dangerous event. That emotional mismatch is what I want you to remember. Do not wait for your fear level to match the hazard level. Sometimes the hazard is ahead of your instincts. Sometimes the most dangerous earthquake is not the one that felt biggest. Sometimes the ocean has to finish the sentence. If you live inland, this might all sound distant, but the underlying lesson applies far beyond tsunamis. Hazards often reveal themselves in layers. One sensor catches one piece, another catches the part that matters more. The person who stays safest is usually not the person who reacts to the loudest signal. It is the person who respects the full chain of evidence. In earthquake country, that means knowing the ground can be only the first messenger. So let me leave you with the practical close. If you are ever on a coast exposed to tsunami risk and you feel strong or unusual shaking, do not waste the next few minutes deciding whether it was strong enough to count. Move inland or uphill. If officials issue a warning, follow it fast. If the ocean suddenly drains away, do not walk out to look. That is the shoreline pulling the trigger. And if you want one sentence to remember from this entire video, make it this. Some earthquakes tell you their story to the ground, but the worst ones may need the ocean to reveal the ending. If you made it all the way here, you already know more about tsunami earthquakes than most people. Scrolling past a breaking news headline. You know why magnitude is not the whole story. You know why DART sensors matter. You know why some events create weaker than expected shaking, but larger than expected waves. You know why warning systems have to act before certainty arrives, and you know why the phrase ocean sensors detected something much bigger is not clickbait when it is used carefully. It is the story of a real hazard pattern measured in real time by one of the most important quiet technologies in disaster science. Like the video, if this kind of calm, evidence-based breakdown is useful, and subscribe with notifications on, because the next part of this story is the one that keeps coastal hazard experts awake at night. What happens when a tsunami source is so close to shore that even good sensors still do not leave much time? And I want to hear from you. If you were staying in a coastal town tonight, would you know your route to high ground without looking at your phone? Drop your answer in the comments. I read every one. Stay safe out there. I'll see you in the next one.